Greetings A-level students, welcome to a little explainer video where we're looking at how we represent cells and we're going to calculate the cell EMF in two different ways, and you can pick which method you prefer. So we've got a chemical reaction between solid nickel and I2, and when I'm looking at this question I'm seeing that the nickel's oxidation state is increasing, so this is being oxidized, so therefore the I2 is being reduced. And we need to draw a label diagram of the experimental setup for measuring the standard cell potential of this reaction, including apparatus details, and then we need to calculate the cell potential from the information provided in the table. Okay, cool. So the most negative electrode, which is the nickel electrode, is going to form our anode because that's where oxidation takes place. And what this shows is that relative to hydrogen, nickel is more likely to give out electrons because of its negative reduction potential. So relative to hydrogen, nickel is going to give out electrons because remember the standard hydrogen electrode has this value of 0, and relative to that, nickel is more negative, so more likely to give out electrons compared to hydrogen. The flip side of that is I2, on the flip side, is more positive than the hydrogen electrode, so it's more likely to accept electrons. So that means the equilibrium for the I2 is going to be over to the right-hand side. So what is happening? So the nickel is going to be oxidized, and the I2 is going to be reduced. Okay, so let's think about how we're going to draw this. So by convention, the more negative electrode, i.e. the anode, is going to be our nickel. And that's going to be a solid lump of nickel, okay? So you've got a slab of some nickel, and it's going to be in solution of its ions. Okay, so it's in a solution of its ions. So this could be nickel sulfate, AQ, and under standard conditions it's got to be 1 mole per decimeter cubed, okay? And this is my nickel metal, so my nickel solid. Okay, and then what we're going to do is we are going to draw the other half cell, which is going to contain I2 solution. Now, have a look at this, inspect this. We've got I2 and I minus, okay, in solution. So we don't have a solid slab of I2, so we need some sort of electrode for this reaction to occur on. So we are going to use a platinum. So we're going to use a platinum electrode, okay, because our species are both aqueous here. So this is a platinum electrode. So then our solution is going to contain, it's going to contain I2 and I minus. So we've got I2 aqueous in here, and that is going to be 1 mole per decimeter cubed. So we could have had Ki solution in here, and we also need 1 mole per decimeter cubed of that, because that's going to give out the I minus, okay? So then what do we need to do? We need to connect these two half cells up, because two halves make a whole. So these are my wires, and these guys are going to be connected to a high resistance voltmeter. So this is my high resistance voltmeter, so I don't want any current flow. There's going to be a tiny amount, so I'm trying to limit the current flow. So high resistance voltmeter, because I'm literally trying to measure the difference in potential between one side and the other, okay? So I also need a bridge, and a bridge connects 2 points. So what I'm going to use is a salt bridge. So here is my salt bridge, and this is some filter paper saturated in some sort of electrolyte, so it could be KNO3 solution. Let's go for KNO3. It's a safe bet. And what this does is it allows ion conduction or ion flow through the salt bridge to maintain charge neutrality so that the cell is complete and works. Okay, what else do we need? Well, we actually need to quote the temperature, right? So it needs to be 298 Kelvin. So it needs to be 298 Kelvin. Do we need anything else? We've quoted that the concentrations of the solutions are 1 mole per decimeter cubed. Okay, so 100 kilopascals as well. So it's at atmospheric pressure. Okay, cool. So, are we missing anything? Is everything correct so far? So I guess the next aspect is, let's write the conventional cell notation for this. So this is going to be nickel, solid, phase boundary. So nickel, 2+ aqueous salt bridge. So remember, it goes reduced, oxidized, oxidized. So what is the oxidized form? That's going to be I2 aqueous, and then that's going to be I- aqueous, because that's a reduced form. And then we need a line, because I've got a platinum electrode which is solid and it's in a different phase to the I2 and the I- because they're in solution. You can put the 2 if you want. Okay, sorted. That looks good to me. That looks good to me. Okay, so that's a conventional cell notation, because if we think about this, the nickel gets oxidized from nickel metal to nickel 2+, and the I2 gets reduced from I2, gains 2 electrons, so forms 2I-. Cool, and we've got a platinum electrode for the electrons to build up on and then move through the circuit. Great, that looks good to me. So what is E cell going to be? So let's just finish this off. What is the cell EMF going to be? Well, there are 2 ways to do this. What I would do, you can break this up into the oxidation and reduction reactions. That's how I'd approach these questions. So the oxidation is nickel to nickel 2+ plus 2 electrons. And that value is not going to be minus 0.26, because that's the reduction potential. So EOX is actually going to be plus 0.26 because the reverse reaction is happening. And then my reduction reaction is going to be I2 plus 2 electrons forms 2I-, and E red is going to be that value because it's already moving from left to right, so it's already given as the reduction potential, so we're just going to quote that value, okay? So E red is equal to plus 0.55 volts. And then remember, the overall reactions is going to be the oxidation and the reduction added together. So if we add these together, we're also going to add EOX and E red. So therefore E cell is EOX plus E red. So it's going to be plus 0.26 plus 0.55. Okay, and if we process this, E cell works out as, what do we get? So we're going to get plus 0.81 volts, so feasible. The other way you could have done it is method number 2. You could have just said that E cell is E red minus EOX, and you don't change any of the signs here. So E cell is equal to the reduction potential for I2 minus 0.26, but what you're effectively doing there is changing the sign, right? So that also equals same thing, just 2 different ways and 2 different approaches of doing it. Whichever one gets you the answer every time, that's the method that you need to go with, okay? All right, so we have represented cells, talked through all the different parts of representing a cell. So if you have species which are in aqueous solution or gases, you need a platinum electrode, you need wires, high resistance voltmeters, and salt bridges. And then we've also talked through calculating EMF as well. Okay, just looking at some of the examiners' comments, they didn't draw. A significant number of candidates or students didn't draw simple circuits. Now, a lot of candidates scored the mark for the nickel electrode, but fewer candidates scored the marks for the platinum electrode. Okay, so lots of people didn't draw the platinum electrode. And if you've got a species in aqueous solution, like we have, or gases, then you need a platinum electrode for the reaction to occur, or need a surface for the reaction to occur on. And remember marks for conditions. Most people quoted 1 mole per decimeter cubed, blah, 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 blah. What are some common errors? The electrode's actually not entering the solution. Well, they can't just jump. You need the electrode in contact with the solution. What else? Salt bridge is not labeled and not entering the solution as well. Solid iodine as an electrode, which isn't a thing. Iodine to be a gas, which is, I mean, we're not vaporizing it at 298 Kelvin. So we're not using a standard hydrogen electrode here. We're just comparing two half cells, right? So just remember what we're actually doing. Read the question, I would say, rather than answering your own question. Okay, thank you for watching. We'll leave it there. Ta-ta.